started almost like a method. And again, we're going to continue this series basically on machine learning. So earlier we did learn basically on the feature engineering techniques, so basically imputation techniques, right? If we had any missing data, we learned basically how we can fill those values, okay? And there are lots of techniques which we used, right? So today we will learn much more interesting things, basically starting with encoding techniques, and we'll end up with lots of other techniques as well, right? Let's see what we can cover today. Okay, so here you can see that we're starting with categorical encoding. So what is categorical encoding as a whole? So if we just look into this, so categorical encoding basically refers to replacing the category strings by a numerical representation. So if you remember if you remember any data set we had, specifically Titanic data set or anything, so categorical encoding or categorical data or variables are basically something which had strings, mix of strings, strings and numbers and so, and those are basically categorical variables which had. Okay, now the thing is you have to understand that sometimes, specifically if you just look into this example, let me just take this here, make it visible. Okay, let's just talk about this one. Okay, here you can see, assume that color is a column, okay, in a Excel or data we have, okay, or CSV format, whatever is good for you. Just assume that within that Excel or whatever we have basically this color column, okay. So this color column basically has this 1, 2, 3, 4, 5 data, okay, great. And all of these are basically, like you can see, red, yellow, green, and so these are strings, right? So these are not numerical things, right? So you have to understand that as we're using machine learning, so we're dealing with numbers, okay? So if we are providing some numbers to a model, we're expecting some numbers as an output as well. So just assume that this is our ML model, something like that, and we're inputting some numbers. Okay, not bad. Okay, we are inputting some numbers, and we're expecting some numbers as well. Great. But what if we have basically values which are string and so? So there are some techniques, obviously, which we can use to make those numbers to from take those strings and make them make or generate some numbers. So one of those techniques are basically these one hot encoding, and so these and this is part of basically categorical encoding. So why we do the categorical encoding is, I believe it's clear, because we are dealing with numbers, but in our column we can have string, and so like obviously the model is not capable of learning from that actually string. Although you may ask like how these LLM models or ChatGPT and others can now easily talk with strings or sentence we provide. So that's again, those numbers are actually decoded, and a lot of things that happens, vector and so on. So we will learn that later on in our series. Okay, great. Now let's focus on the categorical encoding. I hope you understood the concept that, okay, we are converting this string to some sort of numbers. Great. So here you can see this encoding, basically there are multiple techniques which we can use. One of those are one hot encoding. There is one for ordinal level encoding. There is one for count or frequency encoding. Okay, so mostly what you will see is basically one hot encoding is basically used in linear models, and ordinal level encoding is used in tree-based models, and count or frequency encoding is mostly used in Kaggle. You can see. Okay, great. Now let's start with the one hot encoding technique, and let's move on there. Okay, great. So here you can see the one hot encoding. So what's happening here? So in the one hot encoding, what happens is, just look into the strings. Okay, we had them. Now you can see one-hot encoding consists in encoding each categorical variable with a set of Boolean variables which take the values 0 and 1. Obviously, Boolean 0 and 1, which we know, indicating if a category is present or for each observation. Okay, so as in like you will also you have to understand one thing, and that is we will use libraries and so on, and we'll call them and we'll say like, okay, this is the column we are looking into. Take this column and generate actually these Boolean numbers for each of the value. Okay, so we are not interested about how it's generated, why is it is generated. We are not interested about it. Rather, what we are interested is basically what's the output. Okay, we will just think this as a black box. Okay, this is another technique, and if you just want to learn that, you have to learn the library, basically how it's generated and so on. Okay, let's go for that. Now let's look into that. We have rate, two rates, right? So assume that we have called the library, and what this library has done is basically converted this rate to 100 rate. And you can see again, as rate has been converted to 100, if there is again a rate, obviously it will be 100 because for each unique value there is a unique Boolean number assigned. Okay, so for rate it's 100, so we can write that. For rate we have 100. Great. For yellow we have I believe 0 1 0. 0. Great. And for green we have 0 0 1. Great. So again, for yellow 0 1 0, for this yellow 0 1 0, same. So this is how it's generated. Now, okay, so it's basically K. We can if you learn later on the loss of techniques we have in machine learning specifically as well. So here you can see that for each of this one, like rate we have 100, for yellow 0 1 0, and so on. But you can see there are three values, right? Boolean values 0 0 1 100 0 1 0 0 0 1. You can see we have only three values, but using these obviously Boolean values, we can generate how many unique numbers? If I'm not wrong, it should be 8, right? Because if we start with 0 0 0 0 1 0 0 1 1 1 0 0 1 0 1 1 0 0 1 1 0 1 1 1 1 2 3 4 5 6 1 2 3 4 5 6 7, right? Did I miss anything? Oh yeah, I did miss 0 0 1. Okay, my bad. Great. Okay, did miss this one. Should be 0 0 1 and obviously 0 0 0. So we have 8, right? So now the issue is because obviously you can see there are 3 columns now, which is again a burden to the model. There's a new column to compute and so on. So this is something we might not want, right? So this is basically this technique, like if we don't mention anything or don't want it to be optimized or so, it can just create these Boolean values, and it's called basically k variable. Okay, but you can easily see that using this tree, we can actually cover 8 unique values. But if we had only 2 columns, I believe we could cover these values, right? How? If you just look into these, obviously, rather than 3 columns, if we had 0 0 0 1 1 0 1 1, right? As we had only 3, so we could have covered with this only 2, right? So this is another technique called k minus 1 variable. So if we ensure that, okay, we want to use that, so it will use a technique and using that, it will just eliminate a basically column and make it optimized. Okay. So you can just use any of the techniques, but yeah, it's also suggested as well. So here you can see the rate has been assigned 1 0. Okay, this one. The yellow has been assigned 0 1. Okay. And green has been assigned 0 0. That means we have one more room left. Okay. Great. And here we just have used like two columns. You can just add S. Okay. And we have three columns here, or calls. Okay. I believe that should be okay. So we have learned about one-hot encoding. So that's done. One. Now let's talk about ordinal level or integer encoding. Okay, here there is no, like, obviously we have the string value, but we don't have any Boolean value assigned to it, rather just simple strings. Here you can see for red we have 1 assigned, for yellow is 2, for green is 3. That's it, simple as that. Okay, now you may ask, like, okay, why and when we use this kind of things. All of these things actually depend on the context. And also, we have just learned a moment back, like, when we mostly use those things, right? You can see for the linear models, we use one-hot encoding. For ordinal or level encoding, when we're using tree-based models, we use that. And in the Kaggle, mostly the count one. Okay, now let's look for the third one, which is count or frequency encoding. Okay, now here you can see the rate. Okay, rate is twice, right? Rate is twice. So rather than the string, obviously we replace that with numbers. Okay, but this time with some sort of frequency. Okay, let's look into that. So here, like, when this model actually, or when this technique basically learned about this string rate, okay, it found out that rate is here twice, so it just used 2, which is F, frequency. Again for red, it knows the frequency is 2, great. For yellow, it's 2 again, right? 1 and 2. So frequency is 2, frequency is 2. Okay, we have dealt with how many? Great. Now for green, we have frequency 1. That means it appears only one time. Okay, great. Now what we can do is, or what this basic technique does is, basically, you can see we have how many numbers? 1, 2, 3, 4, 5, 5, right? So then 2 is divided by 5, 2 is divided by 5, 2 is divided by 5, 1 is divided by 5, 1 is divided by 5. And that is something we get. Here you can see 0 0.4, 0 0.4, 0 0.4, 0 0.2, 0 0.4. And it can be done using percentage like others as well. So we can just compare it like that. Okay, so this is the value basically. Instead of the string, we have these values. For red, now it's the numerical value is 0.4. For red, 0.4. For yellow, 0.4. For green, 0.2, and so. Right, great. Now we'll learn about another interesting thing, which is called unseen categories. Okay. What is this unseen categories, right? Rather than going for the theoretical part, let's just focus on the data sheet. Okay, assume that we have 10 observation. That means 10 vehicle names, no problem. Mercedes, Ford, Renault, say, and so on, right? I've explained in one of my videos that, in this series obviously, that why we split the data into training and test, right? Again, if I just summarize that, we basically train a model on the trained data set. Okay, so assume that we have 100 data. Okay, we take 80 data from here and take 20 and keep separately keep that 20 data. Okay, then assume that there is a black box. This is a box, which is not black though. I should draw it as black. Okay, great. Let's see if it's black. Okay, something is a black box, something, assume that. And assume that this is a model. Whichever ML model, which we haven't learned any model yet here in the series, right? We'll cover that in later videos. Another thing is that these 80 data, assume that a scientist from MIT has created a model. That's really great. And what you will do is you will provide this 80 data to the model and you will get some thing. Keep it in mind that in general, the machine learning, in general, the basic machine learning which we are talking, we have basically X and Y. Okay, what is this X and Y? So here in the Y axis, obviously we have the Y, and in the X axis we have the X, right? No problem with that. Okay, let's just doing some prediction and others and so in general. Okay, So you will see in most of the data set that we have something called X train, we have something called Y train. Okay, you can see something like X train, and you'll see something like Y train. So what is the main thing, or what we are basically referring to? What we are referring to is basically that X train obviously can be of like one column. Okay, like assume that we have something called age and something depth. Okay, the age, like assume a person's age is 70, and after the age of 70 that person is dead, and it is 1, whereas we are making it up. Okay, and an age is 25, death is no, he or she is alive. Age is 2, might be dead as well. Age is 75, might not be dead, but let's just give it dead. Okay, so from this easily you can understand that this column, we can take this as X train, okay? And this whole column can be Y train, okay? Something like that. So you can plot them depending on that, okay? 70, like assume 2 for 2, okay? For 2, like assume it's 0, right? For 2, obviously this is 2, but and the Y value is 0 here, okay? And for 25, it is 0 as well. But for 70 and 75, like assume it's 70, the value for like 1 here. For 75, the value is 1, like obviously it is 1 for y-axis. And okay, that's how things work. Okay, 225, 70, 75, right? Okay. So these are the things. Okay. So you can understand that, okay, when the age was very, obviously, age is very low, but like, okay, the death is like, okay, the person is not dead in general. But okay, my bad. I believe I made it 1, and yeah, let's just change it to 0 for context. Okay. Sorry. Should remove this. Let's just make it 0. Just to make it like obvious. Okay. As we don't have much more data, we cannot go for a result here. Okay, so just assume that for if the person is of age 2, he or she is not dead. If the person is of age 25, not dead. If 70, 75 is already dead. So what are you learning from the data? We're learning that as the age grows, the person has a high probability to be dead, right? So if now someone comes up and say, hey, my age is 90, my age is 90, like, okay, this one, from here, obviously, if the x value is here, so what will be the value of y? Just keep it in mind, this is the x value, x value, x value, and x value. And for 2, the value for y is, here the y is 0. For 25, the value of y is 0. For 70, the value of y is 1. For 75 is 1. And for x equal, obviously, 90, what will be the value of y? Okay, we are considering this as x and y. What will be the thing? This is what basically we learn by ML models. Okay, that's why we have x data, y data. And then basically when we pass this x and y, what we do is the model basically learns from the data. It tries to understand the obviously why this data behave like this, and so then what we do is this 80 had basically x and y, obviously x train, y train. This 20 had x test and y test, obviously testing data. These are testing data and these are train data. So then again what we do is we pass this x, okay, we pass the x here to the model. Once it learns all of these things properly, pass the x data, we try to find out the y data, that is basically the predicted data from the model. Okay, so let me just make it clear. So this is x train, y train. You just pass all of these and assume that it has learned properly. Okay, learned properly, done. This model has learned properly. You are sure about it. Then what you will do is remove this. Obviously, We are happy that the model has learned things properly. Great. Then we'll pass this X test data and we'll get some Y data, which we call predicted. That means basically for 90, we are just providing 90 here, which is a test, something like that. And we are asking what should be the value. Is it 1 or 0? In our case, it should be 1. Okay, assume that we have passed 90 and it is 1. Great. And you have to keep in mind that we already have Y for this. We know the data. We actually know the result, but we haven't seen that. We haven't showed the model the Y value yet. It doesn't know. Okay, then we will try to compare and assume that for the 90 value, like the 90 means the one unique observation. In this, obviously, for 90, we actually had 1. That means the model actually detected 1 and it was actually 1. That's great. That actually gives the model the 100% accuracy. Like, okay, it can learn, it is learning things properly. Although I'm not right because okay, only by one observation you cannot say that. You have to train and test on thousands or billions of data if you can. And then you can call the model a very good model. So this is how we do work on the models. But now the factor comes in is of, okay, why did I recap these things? Because I have seen that many of the folks who are learning the machine learning model, they just call some libraries and so on, but they are not focused on what is happening, why we are doing things. So it's important because there are a lot of people who can use the libraries, call them and use AI to generate them. But you have to understand what's happening. If you don't know the basics, you will stop one day. Okay. Now let's move on and talk about this thing. Okay. So here you can see that vehicle make, which is a column. Great. As mentioned, we have actually splitted the data into training and test data set. No problem with that. So, okay, now I will do one interesting thing that is not interesting, but yeah, I'll just try to remove this thing so that you can focus much more on this. Okay, great. Let's just focus on this thing. In the meantime, feel free to actually share your learning in the LinkedIn or Twitter, whatever platform you use, or Facebook, and make sure that others who are learning ML can check this content. Okay, because if you are getting help, I hope you can share this content with the others. Okay, great. Now let's move on to this one. Here you can see that, as I mentioned, we split the data into train and test data. Great. Interestingly, in this training data set, we have 1, 2, 3, 4, 5 data. Great. No problem. And we have an ML model, black box. Somehow we have put this, and keep it in mind that this is one column. We're just using this for an example. There is no Y or no X. There is nothing. Assume that there is some invisible Y here. Assume that this is X column. And there's some Y column there as well, but which we are not bothered right now because we are much more bothered about this thing, because you will understand why we are bothered. So assume that we have X and Y and we provided that. Okay, the model has learned properly for each of these value. Great. Now, what is the issue? The issue is when you are using the testing data set, you will see that when we are using the testing data set, you can see there are some values like set, PMW, which we never had in our training dataset, right? Okay. Like it is something like, okay, you are going like, you have a child, okay, and he or she is, or she is in class 4, okay, no problem. Now, you trained that student basically for basically summation of basically 2 numbers. Okay. And whatever the number is, that person can actually, if there are 2 numbers, that student can actually do that. Now, the problem arises when we set a question where there is a multiplication of 2 numbers. Obviously, it's expected that the student might not be able to answer the question. That is the thing. As you have trained this ML model only on this X data, it never learned about this data. So that's an issue. And that is why you can see, okay, so this is a column, and every value we have is basically, can consider them as labels. Okay, labels. And you can see that this seat and BMW, these two are basically real labels for these trains, because there is no seat and BMW in the train dataset. Okay. And obviously, for this test data set, Mercedes and Nissan, if there is, you can see there is no Mercedes and Nissan here. But although it's not an issue for the test data set, because, okay, if I have learned for thousands of questions and there are only 2 questions, there is no problem. But the problem arrives if this is totally out of syllabus, right? That's how the situation is. So real labels. Okay, so yeah, and there's a concept called high cardinality. That means if you have lots of unique values, like you can see within the vehicle make column, we have Mercedes board and so on. So lots of labels that can create some issue, and you will see how it creates the issue and so on. Okay. Now, let's just focus on the thing like, okay, in this scenario, obviously, if we, in this rare case situation, if we use one-hot encoding, because we need to deal with this problem, right? We need to deal with this problem, right? So how can we deal with it? Let's we have learned 3 techniques. Let's use one of those. If we use one-hot encoding in this scene, what happens? You can see for Mercedes, it assigns some value, no problem. For Renault, assigns some value. For Ford, Kia, Nissan, everything, it was assigned when we used basically one-hot encoding in this scenario, okay? But also you have to keep it in mind that obviously these are strings, and so we have just used one of the 3 techniques we have learned, and these were generated. But assume that we have never seen the data, or we never analyzed that there are some obviously real labels, so there is like obviously high cardinality, we haven't dealt with it. Okay, this is the scenario we are basically currently observing, and this is the scenario we will solve. That is what we're learning, okay, just for the context. Okay, you can see for the Ford and others, okay, no problem. There are 5 Boolean numbers that has been done, assigned, obviously as we used one-hot encoding. Okay, this is for the training dataset. What happens for the test dataset? For the test dataset, you can see for Ford, okay, it is good because you can see the 00100, 010. Okay, great. For seat, that is interesting. The interesting portion is that there is 0000, whatever. There is no value assigned. Now you may say, okay, assume that this number was assigned to here. No. In this one-hot encoding, if this particular string was not assigned any value in training, it won't be assigned any value in the test. That's easy. Because for the BMW, you can see exactly this is assigned. And that's an issue, right? Okay. So that means if we use one-hot encoding without dealing with this real level incident, we have to deal with it first. If we don't deal with it and then use one-hot encoding, it's a failure. Okay. So one-hot encoding is a failure for this real level scene. Real level scene. Okay. But obviously we can deal with this scenario, then use this one. So we'll learn about it. Great. So again, other 2 techniques, ordinal encoding and the count one. If we use the ordinal encoding, obviously it is assigned some sort of string, some number. Okay, you can see for Mercedes is 1, for Renault is 2, for 3, for Kia is 4, for Nissan is 5. Okay, no problem. Just don't bother about this for now. Just focus on this. And when for the test dataset, as you can see, for Ford it was 3, right? So it is 3. For Renault it was 2. It was 2. But things which like for the seat and BMW, it's not a number. That means it also can't handle this. That means ordinal encoding is failing here as well. We are missing on some data. As it's string, obviously we'll use these techniques, ordinal or one hot encoding or count, and you can see it is failing because we haven't dealt with the real level scenario. So that's real learning. And again, for this one, for the count one or frequency, you can call. You can see Mercedes is one time, Renault is one, Ford is one, K is one, Nissan is one, no problem. And you may ask, okay, why haven't we divided that by 1, 2, 3, 4, 5, 5? That's not issue. It can be pure number or fractions, a floating number. And again, you can see for Ford, it is one, obviously, because it was one here. For it is not a number. That is it. That means it is again failing. It is failing for the count as well because we are unable to deal with these things, the invisible things. So, what we have learned is if we have any string, we have to use one hot encoding or ordinal encoding or count. We generally use on any of these. But in case if obviously it is string and the whole column had a string, that is what we're meaning. Or categorical, I believe we should say this like categorical variable. It means it has a string, and so we can use one hot encoding or ordinal encoding or count, no problem. But if that categorical variable has real labels, that means after splitting, there are some obviously values which never exist in training. These technique won't give you the result. They will cause issues, right? Okay. But okay, we will deal with these things. But before that, let's just go for the coding portion and let's see how this one hot encoding and other techniques do look, right? Specifically, first of all, we'll start with one hot encoding, then ordinal encoding, and then for the count. Okay, let's go for the coding portion. Hey, so let's comment here, and the whole obviously this GitHub repository link will be provided in the description section. So yeah, you can look into that. Okay, so here you can see into the Titan dataset with lots of columns, right? P class, survived, name, 6, age, and so on, right? So yes, the important one is basically the survived one because what we are doing, the static dataset is basically to try to detect uh, which factors were important. Uh, like, okay, if the person, like, as you all know about the Titanic, obviously, there are a lot of people who died, right? So that is one. That is the thing we have here 1, 1, 0, 0. That means the person survived, the person died, and so on. We have that. And we're trying to find which factors were helpful. Was it like, okay, if the person was near a deck or near something, or if the person had actually paid lots of fare, was in high class, did the person survive or not, or the person, yeah, something like that. Okay, these were the things we're looking into. That's why we have this survived column as Y, and for X, that means the variable depending factor, we have lots of columns which we can take and which we do. Okay, you will see. Let's just go for the code. Great. Here you can see we're saying that we'll use P class, save it as P, purge, 6, embarked, cabin, survived. These columns are something we're going to take. Although these are not all of the columns we're looking into, but yes, we're just currently dealing with these columns. Okay, keep it in mind that this is the Y and all of these Y column and all of these will be for the X column. We'll use some technique, the lots of ML models which can detect the relationship. Okay, so here you can see the values. We can just check the we can actually use the column and you can verify like, okay, if that we have got the values or not. Now let's just look into the thing. I have explained these earlier as well, that will drop the survived one because survived column is something which is for the Y. We are not learning from the survived column. It will be the Y-axis. In the X-axis, we will have all of this, right? So yeah, we are just saying the target is this survived column and drop this from X. That means all of the others are basically the X columns. and test size 0.3. That means 70% of the data will be for the training and 30% will be for the test. That is it. And in my, obviously in the slides, I did show 80-20. So it's better for if we provide these to 0.2, but yeah, 0.3 works as well. So I can see after that, if you just look into the data, you can see we have how many data? We have almost nearly 1,110. Sorry, 1,310, right? So if we just see that, you can see here you can see 916 and 916, 916 data basically for what? For training, and 393 data for testing. Okay, so yeah, this is how it was splitted for the training, and obviously you can see that we have 6 columns here. Okay, great. Okay, for the X, okay, great. Now the easy stuff, well, I'm not going to cover like okay how it's working and so, but just keep it in mind that we learned about imputation earlier, right? Imputation was basically dealing with the missing data. So here assume that we want to assign the this string called missing whenever we have any data missing in any of the columns. Okay, so this is what we do. You can see for the X training data like 969 so 916. Okay, so 916 data. If we have within that, in the sixth column, if we have any missing data, we'll replace that with this, basically the word missing. Okay, and for the test, same. We're basically using the imputation technique, whatever it is. Now you can see if you just look for the data for the training data only, you can see for the cabin the missings are there when we had this for specifically for 501. If you just go there into our data set and verify this one, 501, let's go grade 501. For cabin, right? For cabin, 501, 501 for this one. Although I did look into that before, but let's just verify. Yeah, 501. You can see that, yeah, this is missing, right? This column, obviously this column refers to, you can see cabin, we had some string b5 or whatever, but for 501 we are missing. That means that missing point was basically missing data was replaced with the word missing. Okay, although you can ask like why this basically Excel sheet is not changing because obviously this is in my computer system, but this is not something that has been changed or modified anything, right? That is in the RAM basically. It's basically dealing with that in my computer. Okay, let's just go for that. Okay, so we are happy, right? That we have also verified that there was missing, this column was missing, and we replaced that with this missing. Now, interestingly, what happens is now we can verify. Okay, we can also verify later on that okay how many data are now missing, and so we can do that. Okay, and if you just look into that, you will see that okay there are no data missing because we've already handled that. Now let's look for the one-hot encoding. We are now dealing with the one-hot encoding. Here you can see this is the one-hot encoder which we are using from scikit-learn. We have to use this one first. We have to set auto. Then for the drop, you can use either first or none. If you use none, it uses k variable. Okay, k1. That basically we learned the k. And if we use the word first, it uses k minus 1, which again something we can verify here. I will show you. So as it will learn all of these, okay, just runs on it, and obviously it learns from it, and you can see spurs output should be false, handle unknown should be error. Okay, if there is an unknown thing for the real labels, it will cause error, and that is an interesting thing which we need to know, right? Because you see that we were saying that in case of real labels, if we don't handle about it and then use this one-hot encoding, that should not be good. And this one-hot encoder basically handles this issue. You can say what should be done in case of it found out in real level. Okay, great. Now let's just make it clear. That is, okay, how many unique labels we have now, if you just want to see. So you can see that we have 1, 2, 3, female, male, these things. And these are basically all of the unique uh, labels we had in 6 columns we had for the X, P class, SX, and others. Okay. You can see here we have missing column that is unique. That means we had A, B, C, D, F, G, and so on, right? When we had any missing data, we replaced that missing data, or we added this missing string there. That made it basically a unique label, right? And for here, there was some missing as well. So you can see only for these 2 columns, we had this missing data, right? Great, great, no problem. Now we are happy with it. Now we can just easily basically use the encoder, and you can see that. Now this is the interesting portion. Just keep it in mind, we are using K variable, okay? For the P class, I will show you again. Let's go for the data. Here you can see for the P class, 1, right? 1, right? 1, 1, 1. There are lots of things. 1, 2, 3, right? These are the unique ones, right? If you just come up here, just a moment back, we had 1, 2, 3. This was for the unique values in the P class, right? This is what we see. We've seen. Once we've used the encoder, obviously, which is one-hot encoding, once we've used that, we can see the training data, basically. And here you can see the training encoder, right? The value. You can see the P class has been converted to 3 unique columns now, right? For value 1, I don't know what it is. Specifically, if you just look into 501, let's see what was assigned here. Let's see what was has happened here for 501. 501, you can say it's 2. For 2, what happened? For 2, we have 0, 1, 0 assigned. Okay. For 588, here again you can say, I believe it should be 2 for 0, 1, 0. Right, great, no problem. So for 1, 2, 3, these 3 columns were generated. For 6, female and male, there were 2 columns. Okay. For SIP SP, there were like how many? You can see 0, 1, 2, 3, 4, and many more, right? The lots of columns. But let's just change it. Change it to what? If we, sorry, my bad. Okay. Yeah, here. If we just remove that and great, and run it all. Did it work? Now let's move into here. You can see now this P class only has 2 columns, 2 and 3. That's it. For 6 male, it is only 1 column. Now, wow, how? If the person is male, it should be 1. If it is not, it should be 0. That's it. So that means it is optimized now. Rather than having 2 columns, we have 1 column that is working, and that is good to go. Why should we have much more column and make it computationally tough, right? We should not. That's why this is a K minus 1. So you can see now we have P class 2, P class 3, 6 mil, CBSP 1, 2, 3, 4, 5, and 8. That means the others, if we use the K. So basically, you can also ask why 2 and 3, where is 1? Basically, it first creates the K variables. So there were 3. Then it learns from it and it says, okay, this is minus 1. Okay. Or so. Right. This is how it works. Now then, encoding variable subset. This is not important. That is basically for the, you can, we have already gone through that. That's done. But encoding variable subset for, if you just have a subset and like if you want to use a different technique here and use it on other parts, you can do that. So this is not important. But yeah, I hope you have got the concept of one-hot encoding. Great. Now let's look for the ordinal encoding. Okay, so for the ordinal encoding, what we had, ordinal encoding basically refers to some numbers for some string, right? Great. So here you can see for dataset houseprice.csv, let's look for the data. So here, let's look for the data, and here is the houseprice.csv. So we are bothered about columns like neighborhood, and so I believe, yeah, this is one of the columns we will be working on, neighborhood, and then exterior first. Lots of columns, right? So basically, there are lots of columns. Depending on that, the price of a house is detected. This is what we're basically dealing. Basically, because assume that you have a customer and someone wants to know, okay, someone just provided you these factors and want to know what should be the probable price of this house. So yeah, this is you are a machine learning engineer, and this is what you're learning, and what your task is. So we will basically choose only a few for this demo only, uh, and work on it. And our Y column should be sales price. Yeah, this is the one. This is our Y, and the X columns are X can have multiple columns, and one of those are neighborhood, other can be exterior first, exterior second, and so on. There are a lot of the columns which we can take, but for this demo, we will just choose only these four for X columns and these one for Y column. Okay, so you can also verify the data, no problem. Okay, so you also see sales price, that is basically the for the Y trade. Great, and we are trying to look into uh, if they have any missing data or not. Okay, you can see no missing data for this neighborhood column or exterior first or exterior second. Believe we have, oh yeah, we have only three. Okay, great. Mm, great. Then we can use the ordinal encoding and you can easily see the values for them. So you can see ordinal encoding, that is OE, and it has just created new columns and which has this. And if we go for the data sheet, if we just look into, like, obviously 64, right? Let's just look for that. 64, right? 64. For 64, if you just look into, I believe, also need to look for the, sorry, neighborhood, right? This is the one, M, right? Okay, so 64, 64, oh my bad, M, right? For this one specifically, this string, this ordinal encoding has assigned the value 5. Okay, so what we can understand from here. And for others, this is what it is. So yeah, this is what we can do, right? So yeah, we're just good to go with this concept. Okay, another thing is, obviously, now let's resume our theoretical portion. And here it is. So keep it in mind that when we have used scikit-learn only for this one, but into the GitHub repository, you will find out feature engineering or category encoders, these kind of libraries as well. So in case of error, obviously there is an error, or you can handle that using some user determined value, maybe -1, -30, whatever. But for feature engineering and category encoders, in other cases, it will just show -1. Okay. And for the count encoder, which we haven't shown in our coding lab, uh, when using category encoders or feature engineering, it provides 0. Like this, just focus on this. -1 and 0. But we haven't used feature engineering or category encoders in our demo. So we have just used scikit-learn. So I hope we are good to go with the scikit-learn, but you can check the repository and just giving you a heads up. Okay. Now the question is, how can we can handle the real levels? We'll see that later on, but how we can handle that? Just an easy observation. How we can do that? I believe what we can do is, as they are rare, assume that if we have any real levels, we will consider them to x, whatever it is. Okay, like for example, we have 90 unique strings. Okay, we had that, and I provided that in the training. All of those were in the training data set. Now in the test data set, there were some new obviously strings out there. So the goal should be is basically take those strings and take like if we have any missing one or anything new, we'll consider them as x. We can do that. We can take all of these and group those. We'll see that later on. Okay, grouping real labels. We'll see that. But I'm just giving you some heads up. Now let's look for the monotonic encoding methods. Okay, what is monotonic thing? Right. So monotonic is basically what? Basically finding a relationship. Okay, just look into this graph. You can see that here we have obviously this is x and this is our y, right? You can see it is increasing. Okay, that means as the x is increasing, y is increasing. Then okay, increasing a bit, obviously increasing. But here you can see increasing, then constant or consistent, whatever you say, decreasing, constant. Yeah, x is obviously there, but y is increasing. A lot of things. So these are the things. These are graphs. Like it's increasing and then decreasing. So here for these things you can see like it's almost linear, right? But it's non-linear because yeah, you can see the graph is not uh, like the linear one. This is something like linear. So and you can see x and y they have a relation. As the x increases, y is increasing a lot. So these are monotonic. This is for linear and this is non-linear. But this is not because x, you can see x is increasing and y is decreasing. There's no simple connection. But here, x and y, as x was increasing, y was increasing. Here, as x was increasing, y was increasing as well. But here we don't have that. Great. So these are non-monotonic. These are monotonics, right? Great. Let's listening to this one. Great. This is what monotonic relationship is and why it's important. It improves the performance of linear models. Okay, because you see, what we are doing or what we are basically trying to do is basically feature engineering, right? So we haven't yet started with the machine learning models. Our main task is to make it easy for the models to learn, right? If you can take some measurements and others and then pass it to the models, if they can easily learn that this is our goal. That is why we're learning. So we are making it easy for the models. So yeah, if we can convert the data to like this, have some relationship out there, okay, it's good. So you can see that's what the improve the more performance of linear models. It may improve the performance of tree-based models as well. May okay. Okay, now let's learn about the ordinal encoding, which obviously which is one of the techniques of this monotonic relationship, which we will find basically. Okay, so what is this ordered ordinal encoding? So here you can see that we have some strings, obviously, red, yellow, green, and so, right. Okay, yellow. Okay, so these, one of those are basically we have red like two times, obviously, one and two, and assume that this is our y, okay, and this is something x, okay, and our goal is to like get x prime, like make change to the x column, okay. So for this rate you can see this rate has target 0 and 1 both, right? Just assume that okay, we can write them like this. Rate has 0 and 1, okay. For yellow it's 1 and 1, okay, only one. For green okay, it's 0, no problem. So that's great. So if we have 0 and 1, if you just 0 plus 1, if you sum them and divide them by 2, because we have two numbers as a whole, different, two unique values, that's why it becomes 0.5. Okay, good, no issues. And then as second max, so what happens is then if we just look into the yellow, which has just unique, just one value, right? It is 1. So 1 should be divided by what? 2. No, 1. Because we had this time we had two values. So we took the average. So it's 0.5. But this time it should be 1. For green, it is basically, again, the value is basically 0. Which means like, okay, it should be 0 only. Okay. If we just divide that by 1, it should be 0. No problem. Now we have 0, 1, and 0.5, right? So we can write 0.5 here, 0.5 here for obviously red. For yellow, we can write 1, 1, and for green it should be 0. If we just ordered them, what happens? What happens? Let's just do it. Okay, so what we can do here. Okay, you can see we have 0, then 0.5, then 1. Great. So 1, obviously 1 is the highest value, so we can consider this as label 1. Then this is the second highest, label 2, and this is the lowest, which should be label 3. This is how it is ordered. You can see for 0, obviously, and from this 0, basically, not for this one. Okay, so we have label 3 here, and for 0.5, label 2, and for 1, we have label 1. Yeah, this is what ordered ordinal encoding is. Now let's come up with the benefits of it. The advantage is basically straightforward to implementation and does not expand the features of space, creates monotonic relationship between categories. Okay, this is what we are much more interested. We'll see that later on. Okay, the limitation is basically maybe overfitting. I hope I have discussed in my early videos about this overfitting and when it happens, right? So yeah, we will just look into that. Now let's talk about the mean encoding definition. The second one, I've already gone through one, ordinal encoding, right? Within the monotonic relationship. So mean encoding implies basically replacing the category by the average target value for the category. Okay. So what? Here you can see we have just this time what we'll do, we'll just replace the mean value as label. So this is our y, this is our x, and this is our x prime. Basically, we're replacing this column with this. So the mean value for the red is basically 0.5. For the mean value for the yellow is basically 1. And the green is 0. What is its mean value? Because you can see 0 and 1. We have 0 and 1 for red. So what's the mean value? Is when mean value is basically summation, basically average. Yeah, here what is 0.5. For others, for yellow, it is just one value, 1. That means it should be 1. Okay. For green, it is 0, so 0. So that is it. Nothing that's significant. But yeah, the difference is basically the ordering, right? Earlier we also did the ordering, but this time not this thing. The advantage is again straightforward to implementation, then does not expand the feature space, that's good, and we have some monotonic relationship. Limitations may lead to overfitting just like the other one. If two categories show the same mean or target, they will be replaced by the same number or potential loss of value. This is interesting. Okay, if there are multiple categories or labels which has same mean, then that is an issue, because assume the red had 0.5, black is there and it has 0.5. So yeah, that is an issue because it will, okay, red has 0.5, black has 0.5, and assume for red we are trying to look for a color, and for black we have found white. For red, what should be the color? It may suggest white as well, so it might not be able to learn. So that's an issue. Okay, weight of evidence, which is something you might not see in many videos, right? But it's very interesting. Weight of evidence is basically and was developed basically primarily for credit and financial industries. So it will learn from the columns, like the positives and the negatives, and then it will do somewhat. Like for example, you can see proportion of good events by proportion of bad events. Then we do the log and we get basically the weight of evidence. So let's just look into this one, an example. Assume that we have a column called survived and we have a column called non-survived. And for A class, we have 50 people survived and non-survived is 30. For B, 75, 40, 25, 15, no problem. So as a whole, total survival is 150 and total death is 85. So the total number of people were 235. Among them, 150 did survive. Okay, now we'll just do some interesting thing. That is number of percentage of good or positive. Okay, so what is percentage of good or positive? You can see that this 50 This obviously this is positive or survived, total survived. So this is 50, right? So if we divide 50 by 150, we should have 0.33. 50 by 150, we should have 0.33, right? And if we divide 30 by 85, we should have 0.35. So just an obviously a probability, right? Okay, how many survived? A percentage is whatever you call it, or a fraction, right? For other classes, this works same. Now, as we have the percentage of good or positive and percent of bad and something. Now, what we'll do is we'll just easily get the weight of evidence. And how we get that? We know just log by percentage of something by percentage of something, right? Now, what's the law? Percentage of good event, percentage of bad events. That's it. And after that, we have this minus 0.05716 and so on and so forth. Now you can see these kind of things are very good, or this technique is basically very good for positive and negative things. People survived, people did pay their loan, people didn't pay their loan, and so on. This kind of, when you see this kind of variables, you can use this weight of evidence technique. Okay. Okay, the advantages are creates a monotonic relationship between, okay, this is what we're looking into, good. It orders the categories on a logistic scale, which is natural for logistic regression, so that's good. The transform variables can then be compared because they are on the same scale. Therefore, it is possible to determine which one is more predictive. That's good as well. The problem is overfitting, again, just like before, not defined when the denominator or numerator are 0. Okay, something by 0. If you just do that, is it possible? Okay, in that case, but we're not bothered about this one. Just forget that, as if that it never happened. But yeah, you can just focus on the other things. Now let's just focus on this thing. Okay, let me just take it here. Okay, just keep it in mind that ordered in when we use this ordered ordinal encoding, the targets are basically kind of binary values or continuous values. For mean encoding, it can be binary or continuous, but for weight of evidence, it should be binary. Okay. So yeah, these are the things you need to keep in mind when you want to use these techniques. Okay. Now let's focus on the last one, the real labels and high cardinality. So we have earlier seen, like, okay, when this happens, and we've also seen what the scenario basically is. Now let's go through a consequences basically. Okay, assume earlier we just had one column, right? Now we have two columns. Assume this is x1, this is x2. So this is x1, this is x2, and again for this one x1 and x2. The training, you can see Mercedes, Citroen, and Nissan. These are something that is missing out here in testing. There is no problem because obviously in general we have trained in lots of data. Okay, that's good, but we have some missing data. Okay, some missing data. That means see Toyota, BMW, and never here, right? So in general, if this happens, like data is not here, it might be overfitting. And again, if data are there but it is not in the training, it basically can create aliasation. Now, how can you solve this issue? Let's see. We can group them, right? We can group them, the rare ones. This is what I say, like maybe create a new column or new label and just say, okay, if you just find them out, just consider them as this X or Y, whatever. So for example, if you just look into this graph, you can see these are columns. Obviously, these are some sort of columns we had in an Excel or CSV, whatever you call it. And this is in X and this is in Y. Okay, compared with something. We can see these column has lots of value and gradually decreased and decreased and decreased and so on, right? Until this plywood one, it is good, right? Great, no problem with that. Then after that, you can see it has been decreased for a longer period of time. Great. So what if we can take these like the smaller ones, like assume that someone like our manager said, hey, set a goal like 0.05. If any value, if any column has value less than that, take all of those, create a group. Okay. So here you can see that what we can do here is this column is here, no problem. We haven't changed that because it has values greater than 0.05, no problem. This metal SD, again, this, okay, it worked. And HD board is there. WD, STNG is there. You can see the plywood is there. Now you can see there is another column. What is that? It's called rear. We can name that anything. And it consists of all of these columns. Okay. And all of this we have taken all of those and created a group. Interestingly, now the summation of the values are basically is greater than 0.05. That's great. But now you can see that the graph looks better. Now, if I just remove these things, like for example, okay. We are looking for the monotonic relationship, right? You can see it was increasing, decreasing, and so on. There are a lot of zigzags, right? But now you can see decreased, increased, decreased, increased, decreased. So the zigzag has been, there is less zigzag, right? This is important. And we can see some sort of relationship compared to this. At least it's better now, right? Great. So grouping real labels, when you do that, you can go for one-hot encoding of frequent categories or grouping real labels. You can just use any of the techniques. Okay. So yeah, we have just used this one, grouping real labels. This is an example of this. Okay. Example. And we can also use another technique. We see basically for the one-hot encoding one, you can see. So one-hot encoding of top categories example. What you can do here is, for example, assume that obviously we have London, Manchester, and Leeds, these cities, no problem. So London has 1000 observation, Manchester has like 500 observation, Leeds has 200 observation. So that's great. These three. The number of top categories determined by the user. So here you can see using the 100 encoding. Here 100 means a person is from London. Okay. Then 010 is what? Means he's from Manchester. Great. Then 001 means the person is from Leeds. Great. Also, this is 000 means the person does not belong to these three cities. So rare one. You can handle this one. Just look into here. If you are not clear here, we can just verify. When for London, if you just set this parameter to 1, this says the person is from London. Okay, assume that we're trying to look if the person is from these three cities or not. For Manchester, these values are 1. Okay. For Leeds, these values are 1. Okay. But what if for these ones, we have 000. What's that? That means the person is from any other city rather than this London, Manchester, and Leeds. Right. Okay. So this, again, this one-hot encoding can handle this one. But interestingly, what happens is that we can use that. But we also have to keep it in mind that, for example, we have dealt with it earlier. If you just go here, we've seen that this is an issue because sometimes it can be issue, sometimes it might not be. This totally depends on the scenario actually as well. You can see for this one, like for seat, it was 000. That means it never learned about this thing, this data seat or something. So 000. For BMW, same. Okay. Now using one-hot encoder, you are also seeing a technique that is, if there is any new thing that comes up, you set it to 0000 or something, whatever it is. Like obviously all 0. So you're basically in a way grouping them, right? So seat and BMW and BMW, they have been grouped and they have been assigned 0, 0, 0, 0, 0. That's it. So you can group them using monotonic encoding. That's what has been said. Earlier, we have shown you like, okay, that's an issue, obviously. But if this, this totally depends on the scenario, okay? Like, if you are bothered about those two strings as well, you might not go for that. If you're not bothered, you just want, okay, these are real labels and you're not bothered, you just want to know how much percentage, how many people come from the real cities. Then you can just group them. There's no problem. This totally depends on the scenario. You have to understand that. I hope you will understand that later on when we go more into the models. Okay, great. And another is obviously grouping the real labels, which we have just seen, right? You can just group them based on that. Maybe this maybe is the limit for the one. So you can see there are like 1, 2, 3, 4, 5, 6, 7 columns which will be there obviously, and all of the other which is below that or equal will create a new one. Okay, so you can just do that easily. So you can do that. Okay, now interestingly, let's just learn from some scenarios. Okay, for example, here this straight column has two values. Okay, assume that it has two values. One is PAVE and one is GRVL. There can be any value, maybe some random strings, and 99.5% times it is the word PAVE is there, and like very less percent of times and GRVL the word is there. Okay, great, no problem with that. Now, if you talk about another column which is well, so this column has four values. You can see 62.36% time it has the value TA, 33.2% time GD, and much more X and FA. For this column, same goes for that. There are lots of values here, and like I believe this is the highest one, right? And others are there as well. Okay. Now, again, talking about the grouping word, how you can handle this scenario. What you can do here is you can see that as we have just two PAVE and GRVL, so it is not a issue. Okay, so PAVE is the highest one, 99.5%. So GRVL is very rare thing. Like you can assume this scenario just like this: STRWT straight. This is the column, and we have like this thing: PAVE, and GRVL and PAVE, and so on. Lots of PAVE, very few GRVL. This straight. So yeah, we're just meaning that. Okay. So in this scenario, okay, we can consider this GRVL to this real label. We can consider we replace this GRVL and use this word real. Okay. For this scenario, we had 4, but you can see two of the time we had 62.6 and 33.2. You will see it almost consists 99% or 95%. Sorry. Okay. So we should use those two, no problem. But these two has very few percentage. So we can take them and group them to a new label called rare. Okay, great. So same goes for this one. Okay, and if you just look into this one, okay, this column here, you can see that you can again, if you just look into that, I just mentioned earlier that if this is our label or the least value, if any column has value less than this, we'll take all of those and create a real column. So you can see these NMs is there, the first one, and this second one is there. This Old Town is also there. Word is also there. Then Sawyer there. Summerist. Basically the city names. And the Gilbert. Gilbert. Yeah. Okay. And all of the other cities, like, okay, it took all of the other neighborhood basically and sum them and created a real label. Interestingly, that real label has now more than all of these ones. Okay, so it depends on the scenario, right? The scenario was basically, the interesting portion was this limit. If this limit was basically near this, there might be only, like, if I just remove this one. Okay. Okay, if the scenario was like that, the situation would have been like, we would only take this 1, 2, 3, 4, 5 or 5 neighborhood and create a real label. So it depends on this value. Okay, so it depends on the scenario and others. We'll see. Now let's talk about another concept, which is basically the variable transformation. Okay, variable transformation, very interesting thing basically. So before starting with this, you have to understand that in nature, if you talk about statistics and others, if you work on that, you'll see if we collect the data and create distribution, naturally things are basically in the normal distribution or Gaussian distribution. This is how the world works. Most of the things we cannot predict, but you'll see if we just create a graph, the natural things, you'll see normal distribution. That's why we call it normal. And in our data, if we are working in machine learning models, we'll see how the data looks like. And I have already covered about this skewed and Gaussian normal distribution graphs, and so why it's important, how we can work on it. So sometimes it can happen that, like, a specific column, like maybe called age, has lots of value, and if you just create a graph, you'll see that it's maybe right skewed or left skewed or something like that. But we might need to actually convert it to normal because it is the best practice, right? And we can do that. So the question is, how can we do that? So these are the techniques which we can use to change the distribution from skewed, right or left skewed, to right or left to Gaussian or normal distribution. Okay. So we've already covered this kind of topics, like what is this right skewed or normal distribution. So if you haven't seen that, feel free to check the previous videos. Okay, great. So look, there are multiple techniques like logarithmic, powered, Box-Cox, or Yo-Johnson. So like when the assumptions are not made, we can't fully trust the prediction of the model. What can we do? So in basically the linear model, there are some assumptions. What is the linearity? The normal distribution errors. You can see residuals are random and normally distributed with a mean of 0. These are some assumptions in linear models. So homoscedasticity. At each level of the predictor variable, the variance of the residual term should be constant. So if you're not familiar with any of these, you should actually check the previous videos. Okay. So when we are working with these linear models, as it's expecting these, the normal distribution one and the linearity and others, we have to convert the skewed and others to normal distribution. That's why we do this kind of changes. And this is what we do. But which variable can we transform? We can transform the target variable itself when its distribution is skewed. So transforming the predictor variables very often helps meet the model assumption when the raw data does not. So yeah, it's basically trial and error, but then again, there are multiple techniques. Let's just look into that. So let's go for the logarithm one. So this is the log. So what we do is, here you can see this is a skewed distribution. Once we have used the logarithmic technique, we got a normal distribution graph, almost normal distribution. Okay, so just an example for you. What is a normal distribution? Now let's start to create a line basically. Not sure. Okay, great. So if we just create, so it can be like this, or can be something like this. and normal distribution should be just equally like this. Okay, in the middle, near the mean, most of the data should be near the mean. Okay, here we'll see that. Um, let's just remove these things. It's clear. I hope you understood the concept so far. Great. So using logarithmic, you can see I've gone from skewed to obviously the normal distribution using reciprocal. This is the formula. Using that, you can see like it was just the data was in the left, and here you can see the graph has been changed and lots of data in the middle. And yeah, this is what we can do. Square root, you can see for a square root here again. Here. Okay, for the square root, obviously, you can see the first graph, the left corner did not follow the red line. You can see the first the first graph, left corner did not follow the red line. So this is a red line. So you can see it's almost crossing here. And but after the transformation, after we have gone through this square root one for the QQ plot, although you can see that these are all basically after the transformation, but you cannot see any difference here. But you can see if you just look into this QQ plot, you can see now this data is in between this red line, right? It follows the line, and this is what we're looking into. And QQ plot is something, if you haven't learned, I hope you will look into that into the internet. Okay. Now then we have arc sign. So using that, you can use that, and you can see this was data to the left. Now it's almost in the middle. All of these data are basically from skewed to, like you can see from here, it's totally in the left, and now you can see to the middle, and so yeah, you can use that. And again for the power one, we can do the same as well. Now there are some transformation techniques basically, obviously we haven't gone through, obviously this box-Cox transformation. So how many did we cover? We've talked with logarithmic, power, and others, many more. And then let's talk about box-Cox and this one. Okay. Interestingly, box-Cox transformation basically covers all of the other which we have talked so far. So this is the formula. Great. And here you can see lambda. And if we set this value to 1, there is no transformation. If 0, logarithmic. If -1, reciprocal. If 0.5 is the square root, and cube root, and so on. Okay. This box-Cox transformation is basically suitable for positive variables. Okay. So if the column has positive values, it's good. But when the variables are not strictly positive, that means there might be negative or something, we can add a constant out there or use this one, yaw junction. So yaw junction is basically the same, but there is some sort of constant right there. So yeah, this is how it works. So you'll see if the variable x is strictly positive, then the yaw junction transformation is the same as the Cox power transformation of x plus 1. Okay, before we go for those ones, obviously for the variable transformation, which we just covered, before that we have some other things, so like ordered, ordinal, encoding on mean, or weight of evidence, which we haven't seen so far. So let's go for that. So within this, let's just minimize this, and okay, let's open this one again. Categorical. Within that, let's just look for the pandas one, ordered, ordinal, encoding. So as you know that using these techniques, we're looking for the monotonic relationship. That means x and y will have that, and we'll try to look into if there is a connection. Okay, and we'll try to look into that because we want to find a connection before we are passing these through the model, right? Great. So using the ordered ordinal encoding, I'm not going to explain each and every line. Okay, I'm just going to look for this graph. Okay, so you can see before that, before we use this technique, we have this graph which is does not look good, up and down and so on, right? After we have used the ordered ordinal encoding, you can see what? You can see that we can see on if the neighborhood is in X, that means sell price is in Y, it's increasing, right? Some non-linear, can be linear, not linear totally, but monotonic relationship. Okay, again there, okay, increasing, that's good. So before that, all of these were basically had something like this, zigzag, loss of zigzag. But after this ordered ordinal encoding, it is better now. So there's a high chance that our model will get a prediction, get a connection between these two. Great. Then mean encoding, same. Before that, you can see, okay, so much, and this was decreasing, and yeah, decreased. Great. So after that, using the mean encoding, you see, increased. Great. So yeah, we can just do that. And weight of evidence, we just look into that. It's important that we're dealing with, we're working with the Titanic data because there is things called basically survival, right? Survival means death and living as well, so positive and negative. So yeah, you can see before that, not good relationship, decreasing and increasing. After weight of evidence, you can see what? Yeah, increasing. Great. And this is for basically for the test data, so we're not interested, it will be the same. Okay, so yeah, using these techniques, all of these three techniques, we got some good results. We have some good connection between them. Now let's look for the real levels one, like for the scikit-learn. If we use one-hot encoding, basically for grouping them, we can use them. Okay, here. So we have used 1, 2, 3, 4, 4 columns. These three are for the X and this one is for Y. And that's good. Sales price is basically for Y. And as mentioned, these three are for X. No problem. One-hot encoding for top category scikit-learn. Okay. Here, this has been used. Neighborhood called CR and so on. So there's nothing new to look into here because as mentioned, 0, 0, 0 and 0, this is going to be only all of the values should be 0 for these columns if there is any value that is new to this data. That's it. So okay, so there's nothing to worry about. I believe this is 0, 0, 0, maybe 0, 0, 0, 0. Okay, yeah, this is for Old Town. It's different. Edward names Old Town. Okay, great. Yeah, I got it. Okay, so we can just look into that. You can verify with the Excel sheet, which will be provided, which is also provided into the GitHub repository. I have shown you earlier how to verify that. Just go into here and go into this. Okay, but keep it in mind, these are generated using one-hot encoding. That means there are more column now here compared to we had only few columns out there when we started. We just had what, 3 columns, I believe. Yeah, these 3. And this is for Y. We are not working with this one, but both for these 3. Now you can see lots of columns basically generate for neighborhood, right? And then for exterior first, right? And then exterior second. Okay, lots of columns that has been generated. Okay, great. Now the interesting one, which we just have seen for the logarithmic transformation. Okay. So QQ plot of this column. So if you just look into here, matplot, so stats, no problem. Diagnosis plots, okay. Check function. You can see the data is not in the middle, right? It's to the left, right? And this is a QQ plot basically, and this does not cover the red line. Great. After the transformation, what is happening? The data is almost into the middle, and this line is basically very near to the line. That is what we're looking into for the logarithmic transformation or whatever it is. For reciprocal, again into the left is near, it's very good QQ plot though, but again after that into the middle and very much into the left. So for the QQ plot, this is our goal. We want to fit our data to this linear line. Okay. For square root, same goes for that. You can see we have already seen that example into the slides. And after that, okay, sorry, this has not been changed. So yeah, after this one, square root, you can see it's into the middle. Right, great. Power transformation, which we haven't seen any graph into the slide. Again, into the left here, and after the power transformation, into the middle and into covering the line. If you just look for this box cost transformation, which is very much, which works for the positive values only. These are the data you can see to the left. It's like, okay, not totally to the middle, it's like distributed to the left, so on. Okay. After the box source transformation, into the middle, somehow increased into the middle, into the right though, but not to the right, because yeah, you can also assume that into the middle it is, but yeah, somehow better into the middle, that's good. And the after QQ plot, and this is the before QQ plot. Okay. For Joule-Johnson transformation, which covers basically for the negative ones as a whole, this was the before one, and after that you can see that yeah, it's better into the middles, just like the box cogs. And if you look for the arc side transformation, before that just into the left and others, right? But after that, what happens? We just delete this one. It is into the middle, left, but into the middle. Just if you just compare the early and so, this will mean compactness here. Totally into the left, you can see right here, right? But after that, you can see not totally left, right? These values have been, there is no values here, and data is somehow normal. So now the question might come up is, can you totally make it normalize from skewed to others? We cannot totally make that. We try to do that, but it's like, okay, we're trying to do the best things. That is it, right? We're trying to do the best thing before we run into the model. That is it. Okay. Okay, we've gone through that, gone through a lot of the concepts now, and yeah, I hope that is it for this video. And in our next video, we'll cover much more stuff, so obviously starting with this one. And then we'll talk about the outlier handling and daytime features, feature scaling, and that should be it for our feature engineering. Okay, so yeah, thank you so much for watching this video, and I hope to see you in the next video.